Okay, guys, can you hear me?
Yes.
Can. Okay, good. Okay, so let's we continue with the ideal gas. The day we discussed about we introduced with ideal gas. So we talk about what is meant by ideal gas. We introduced with you PV over T is constant, which you know learn in your Form 5, and a new two formulas, PV equals to nRT and PV equals to nKT has been introduced. Okay, first, what is meant by ideal gas? It's a type of gas that obeys gas laws at any pressure, volume, and temperature. Okay, so it's an ideal gas. Okay, so we did this up to here. So today's lesson is about, we talk about Brownian motion and we derive it. Okay, so that I go to the slide. Let's skip this. Examples all I skip. Okay, so Brownian motion. You learned this in the early studies, right? Brownian motion is a proof that the air particles are moved randomly. Okay, Brownian motion is a proof that particles of matter are constantly moving in a random manner. The motion was first observed by the Robert Brown in 1827, and later explained by Einstein in 1905. Yeah, Einstein explained that the continuous random motion of smoke particle in the cell is caused by the constant bombardment of the smoke particle by the very smaller higher molecules, which are moving endlessly in the random manner. Okay, so in the Brownian motion, what is the observation? What is the conclusion? In Brownian motion, what has been observed? The dust particle move in a jerky manner. Okay, that's the observation. Some students said, what is the observation? They said the air particle move randomly. That's not observation. Observation, what you observe, what you saw in the experiment. The one you saw is the dust particle is the one moving in a jerky manner. Okay. Then what is the conclusion made? Under conclusion, you have to say that because the dust particle was continuously colliding with the air particle, therefore air particle move randomly. Okay, so that's the conclusion. Okay, so don't get confused with the conclusion and observation. Okay, like here, so you should know the conclusion and the procedures lah. The cell bright illuminated microscope to use to focus on the small particle. Bright specks of smoke particle are seen dancing smoke cells. So it moves in a jerky manner. This is the observation. Conclusion: the motion of the smoke particles is evident that the air molecules are also moving randomly. Okay, so that's about Brownian motion. Okay. Okay, now, as I said, scientists know that what causes collision of the what causes pressure to the container is caused by the collision of the particle to the wall and rebounds back. The particle experiences changes in momentum, therefore force is exerted to the wall, so pressure is exerted. So they want to get a formula in terms of speed of the particle. Okay, to develop that formula, which I already told you, the formula is this: PV equals to 1/3 nmc square has been discovered. But to develop this formula, they did lots of assumptions. These are the assumptions they made so that this formula is correct. Okay, you need to know at least 3 assumptions they made. Kinetic theory of gases, 3 assumptions you have to remember. The first assumption is the gas molecule made of the gas particle made of. The gas consists of a very large number of molecules. I can tell you the important one. The first one you can tell is about a collision. The third point. The collision of the particles are perfectly elastic. Okay. Next, you can remember is the fifth one. No intermolecular attracting force between the particles. Okay. So collisions are elastic. No intermolecular force between the particles. And you can talk about something which is neglected. The volume of the molecule is neglected compared to the volume of the container all the molecules, you combine them, the volume of the molecule is too small compared to the volume of the gas. These all are assumptions. Another one, the molecules are constantly moving very rapidly and randomly. Okay, so these all are kinetic theory of gases. Okay. In exam, so far in past years, they asked 3 assumptions. What are the 3 assumptions of kinetic theory of gases? The one you remember the one neglected. We talk about intermolecular force is neglected. Volume molecule is neglected compared to volume of the gas. Okay. Then you say collision is elastic. There is no intermolecular force. Okay. Okay. Now the longest derivation we're going to talk about how they got this formula now. Yeah, how they got this formula. Okay. So now the derivation. Okay, this is going to be like a 1 page of derivation. Please try to focus here to understand how they got this formula. Okay, first they consider a box, and they consider only one particle which has a mass of m moving to the right with the speed of cx. Cx is the horizontal speed. That's why they put sub x, cx, the horizontal speed. So consider one molecule of mass m moving towards phase f, and x component of the velocity, the horizontal component of the velocity is cx. Its momentum in x direction is mcx. Okay, m times cx is the momentum to the right. Okay. At phase 1, we are just talking about the pressure on the phase 1. We want to get the pressure on the phase 1. At phase 1, there is a perfectly elastic collision that the momentum is reversed to negative mcx. Yes. And the particle collide and bounces back. The particle will experience, the momentum will change to the particle moving to the left now after collide. So now the momentum it possesses the mcx but negative. That's what I've written here. Negative mcx. The result in this momentum change of, so what is the momentum change experienced by the ball? Mcx minus negative mcx, so 2 mcx. This is the momentum experienced by the ball. Changes in momentum. Okay, or we can say this is the same momentum change experienced by the wall. The wall also experienced the same changes in momentum, the magnitude, same as 2 mcx. Okay. So after colliding with the phase 1, the molecule travel at a distance of 2L. The molecule, the box horizontal distance is L. All are L, it's a cube. So after colliding with the phase 1, after the particle collide with the phase 1, the molecule travel a distance of 2L. Why 2L? Because the particle must move to the left and bounces back again to the right. So L, you have to travel 2L to collide back in the first surface. We just want to find pressure of the first surface only. So after colliding with phase 1, the molecule travel a distance of 2L. You have to travel a 2L before it collides with the phase 1 again. So this time, the time taken, the time taken for each collision is 2L over Cx. Yeah, Cx is the time taken for every one collision. Okay. So by Newton's second law, the force is change in momentum over the time. You want to find the force, okay? Change in momentum over the time. Change in momentum explained by the ball is 2 mcx. The time taken is t, okay? 2L Cx. So we get mcx squared over L. Okay, this is the force. What is m? M is mass of one particle. What is Cx? Is the horizontal component or the x component of its velocity squared. What is L? The distance, the horizontal distance, okay, between each wall. Any question, guys, from here? Okay. So we get momentum, we get force. Now from force, we want to get pressure. Okay. So what is pressure? That's the next slide. The pressure exerted by that one particle, only one particle. The pressure exerted by one particle is F over A. So F, just now we got the formula beside, divided by the A. A is actually L times L, so it's L squared. L squared. So L up here has become L cube. L cube is the volume of the container. So mc squared over L cube is the pressure produced by what? Pressure produced by one particle to the wall, to the number one wall. Okay. Now let's see, go for more practical solution. Suppose we have n molecules. Let's say one container not only have one molecule, it can have lots of n molecules. Let's say it's n molecules. So all n molecules of gas, what is the total pressure you're going to exert to this wall? So what do you do? The mcx squared over L cube. Every molecule has this value, mcx squared over L cube. But the cx squared, everyone have a range of c, range of c, speed, horizontal speed. So you put a ncx squared, ncx squared. Cx squared is the horizontal component of the velocity for all of them. N is the number of particles. Okay. Therefore, the pressure formula tend to become Nm Cx squared. The C here we put this sign, the sign like this. Okay. This sign we call it min. It's the min speed. Okay. This sign is min. It's a min square speed we call it. Average of the all particles. Okay. In science, they found that all particles in a particular temperature all move in a range of speed actually. So we want to find the average speed. Average, this is your mean speed, average speed. Okay. So we are almost in that equation formation. Pressure is found to be more number of n, more particles in the container, more pressure, more massive the particle, more pressure, more faster the average mean speed, more pressure. But if the volume is too small, pressure also rises. Smaller the volume, greater the pressure. Like a Boyle's law, you see the Boyle's law. Okay, now come to the important point. However, the molecule moves in 3 dimensions. Molecule move in 3 dimensions with velocity c. Yes, the velocity we consider here the horizontal component only, but in reality, the mass might move like diagonally into the page or coming out of the page. So any velocity which is diagonally moving diagonally, force moving diagonally, that c will have its 3 components: cx, cy, and cz. Got 3 components. Okay, so this happens. This is how the actual velocity related to its components. There are 3 components. We use 3 dimensional. We are focusing to 3 dimension. Okay. So c squared equals to cx squared, cy squared, cz squared. Okay, they are components. Okay, now important term comes in. Okay, look at this. Since there are large number of molecules, we can assume that there are equal number of moving in each of the coordinate direction. What I'm trying to say is, another word, the cx, cy, zz must be same value. The cx, cy, zz, the cx, okay, cx, cy, zz, their components, the average components must be the same. Why? Why the speed at every 3 dimension must be the same? Because the pressure in all surface is the same. The pressure horizontally, the pressure in z direction, the pressure in y direction, the pressure in x direction, it's all same, right? If you take a box, if you have a box, okay, you contain with the gas, is it the pressure in all direction is the same? It's the same, right?
Yes.
Only this side pressure is high, make this side only get bulged a lot. No, right? They're going to expand evenly. What? That means the pressure in all direction is the same, correct? That means the changes in momentum by the particle in all direction is the same. Therefore, the component of the speed in all direction is the same for the gas. So c squared equals to cx squared plus cy squared plus cz squared. We found that cx squared, cy squared, cz squared is the same. So what do we do? The cx squared, cy squared, cz squared, we make it 3cx squared. All are same, all change to cx. So the cx squared is actually 1/3 c squared. Okay. What we are trying to do? What we are trying to do here? What we are trying to do? Because the formula earlier is only the horizontal component. We want to write this horizontal component into an actual velocity, which is c squared. So how c squared linked to cx squared? C squared linked to cx squared is c squared equals to cx squared plus cy squared cz squared. Because the pressure same is 3cx squared. So we can substitute cx squared as 1/3 c squared. That's what we are trying to do here. Sorry. Okay. So what happened? The formula 1c squared here, we comfortably can change to this. We change to c squared, but we have 1/3. It's 1/3 c squared. So you got the formula. This is the final derivation. Okay. The pressure in terms of kinetic theory of gas is found to be 1/3 nmc squared over v. Okay. So let's see the logic behind this equation. Okay. How do you rise the pressure? How do you can rise this pressure? By increasing the number of n. You have more number of particle, number of n great, and n get big, the pressure get big. Next is small m, the mass of the gas, the mass of each particle. If each particle has a greater mass, the pressure get big because big changes of momentum and collide with the wall. And of course, c squared, c squared. How fast the particle is moving forward. The particle moving forward more faster, of course, the greater changes in momentum, greater force, greater pressure. So this c squared, right, has a special name. The speed got special name. The name of this speed is mean square speed. Mean square speed. Okay, the mean square speed is like the average speed of the particles in a container. Okay, the mean square speed increases, the pressure is increases. Okay, and the fourth one is V, volume. When the volume of the container becomes smaller, of course the pressure increases. Why pressure increases when volume gets smaller? Anyone? Why volume gets smaller, pressure increases? The number of collision to the wall rises. The rate of collision rises. Okay, rate of collision rises because the L becomes smaller. When L becomes smaller, the rate of collision, how many times it's going to collide with the wall, increases. So more pressure. More pressure. Okay. So this is the derivation of this equation. Any part you don't understand? Okay, we start from what? We start from a container. We talk about one particle moving forward with Cx. The momentum it possesses is mcx. Then when it bounces back, what is the change in momentum? Mcx minus mcx, 2mcx. This is the momentum change experienced by the particle. Same thing, momentum experienced by the wall, same magnitude. Then time taken to go one collision is 2L over Cx. 2L over Cx is the time taken for each collision. So what is the force exerted on the wall? Change in momentum over the time. And pressure equals to force over area L squared, we put that. Then we now consider n particle. So n comes in. Then Cx squared, we change to c squared. Cx squared is found to be 1/3 c squared. and we place it into the equation. We got a formula. 1 year they only asked this part. I think 2 marks. They asked how cx squared you replace with 1/3 c squared. 1 year came on 2 or 3 marks. So what you need to explain? You need to explain this entire thing. The cx squared equals to cx squared, cy squared, cz squared. This is like 1 mark because the pressure is same in all direction. So you have to give this statement 2 mark. Cx, cy, cz is the same. So cx squared is 3cx squared. Then you can show this. Okay. So now we got a new formula for pressure, taught purely from kinetic theory. The pressure equals to 1/3 Nm V c squared. The c squared is mean square speed. Okay. And now if this Nm over V, Nm is what? Nm, number of particle times mass, is the total mass of the gas divided by the volume of the gas, is going to be the density of the gas. So this is another one formula. Okay. V c squared can be written as 1/3 rho c squared. Okay. So another 2 marks question, you can ask this. Okay. There is 1 year they asked this. How Nm c squared become rho? Rho density Nm over V is the rho. Okay. 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 Now the final part. From this is the final conclusion. This is the outcome of this derivation. Okay. From gas pressure, we found that from the what do you call theoretical derivation, we found that PV equals to 1/3 Nm c squared. Okay. From equation of state, we found that PV equals to NKT. Equation of state. This from experimental data, we got PV equals to NKT. Okay. If these two correct, then we can compare them. So 1/3 Nm c squared should be equals to NKT. Okay. So from here, scientists able to find the kinetic energy of one particle. The kinetic energy of one particle, only one particle. So N has been cancelled. So they want to get half here. So what they do? It times with 2/3. Okay. The times with actually times with 3/2 lah. Times with 3/2. You get this equation. You get this equation. Okay. So from here, you just times here 3/2 lah. Here times 3/2. Here times 3/2. You straight away get this equation. Okay. Why we times with 3/2? 3/2 times 1/3 will give you half. We want to get kinetic energy. So half mc squared, which is the kinetic energy of one particle, is found to be 3/2 kT. This is the most important derivation for this topic. The kinetic energy of the particle is 3/2 kT. So kinetic energy of the particle is found to be proportional to, sorry, yeah, the kinetic energy of the particle is found to be proportional to temperature. When temperature rises, last time you said when temperature rises, kinetic energy of the particle rises. What's the proof? This is the proof. Okay, the kinetic energy of the particle is 3/2 kT. The kinetic energy is directly proportional to the absolute temperature, which is measured in Kelvin, not in degrees Celsius, in Kelvin. Kinetic energy is directly proportional to the absolute temperature or thermodynamic temperature in terms of Kelvin. Okay, so if I ask you, now you're sitting in your room, I'm asking, surrounding you have, let's say, air. How much is the kinetic energy possessed by one air particle in your room? It's last time we thought it's difficult. So we put what information you need to know if you want to know kinetic energy of a particle in your room. What information you need to know? You need to have the mass of the particle. You need to know the mean square speed of the particle. But now you don't need to know these two. You just know use 3/2 kT enough. Use 3/2 kT. Okay. You want to know kinetic energy of the particle in your room. What information you needed? Anyone? What information you needed? You want to find the kinetic energy of a particle in the room. Yes? The temperature. You know the temperature, you can find the kinetic energy of the particle. Okay. Let's say your room temperature now is, let's say, 27 degrees Celsius. So change to Kelvin. Kelvin 27 plus 273.15 degrees Kelvin. So it's about 300.15. So the kinetic energy the one particle possesses is 3/2 kT, 300.15. Whatever answer you get is joule.
So that means that 1/2 mc squared is the same as half mv squared.
Yeah.
Okay.
The c squared is like the v squared. But why put mean? Because it's average c squared. Because every particle has a different velocity. So this we use here is the average velocity. So we call mean square speed, which equal like v square. You can take it like a v square. Okay. So when the temperature is 300 Kelvin, and the temperature is 300 Kelvin, this is the energy you have. Okay, now tell me, in your room, you have oxygen, you have carbon dioxide floating. Okay, you have carbon dioxide, you get nitrogen. Nitrogen, all different molecules, but they are exposed to the same temperature. The oxygen and the carbon dioxide, do they have same kinetic energy or different kinetic energy? In your room now, you have oxygen and carbon dioxide. They are exposed to the same temperature. Do they have same kinetic energy or different kinetic energy? So far, what do you learn from here? Same kinetic energy. Both atoms, although have a different mass, they possess same kinetic energy as long as their temperature is the same. Okay. Do they have same mean square speed?
Yes.
The oxygen and carbon dioxide in your room, do both of them have the same mean square speed? Same or different?
Yes.
Same or different? They have same kinetic energy. They have same kinetic energy because temperature same. Do they have same mean square speed? No, right? Because their mass is different, right?
Yes, yes.
Which is going to be move faster? Oxygen or carbon dioxide?
Oxygen. Wait.
Oxygen going to move faster, because oxygen is lighter, right? Lighter than carbon dioxide. So
Yes.
oxygen will move faster. But both possess the same kinetic energy. Okay. So if you go any different rooms and the temperature change, the kinetic energy of the particle change. If they ask what is the kinetic energy of one particle, the information needed is just the temperature. You know the temperature? You can find the kinetic energy of one particle. Don't get confused. It's not kinetic energy of the entire gas. It's only kinetic energy of one particle. Okay. So any part you don't understand, guys, from here? So this is a very important turning point in science. Okay. The long derivation 1/3 nmc squared has been utilized later for a very important discovery. The kinetic energy formula for a particle is found to be 3/2 kT, and we found that the kinetic energy is solely dependent to temperature. That's the biggest discovery in this topic, ideal gas. Kinetic energy is found to be proportional to temperature. Okay. Okay, now go to this word file. So these are the assumptions you learned just now. Then we did the derivation. Okay, the derivation which end up getting PV equals 1/3 nmc squared, and the density formula. Okay, now please take 1 minute or 2 minutes. Tell me the answer for this. One example, empty slot for you to fill up. Okay, guys, come on, 2 minutes. Okay, guys, so you got an idea. Okay, this is a question to differentiate between mean speed, mean square speed, square root, this root mean square speed. The third one is a special name called root mean square speed, RMS speed. Okay. You know, just now I told you the one in the formula. This is what? This is your, what is the name? Mean square speed. Okay. Mean square speed is the highlight here. A, B, C. Which part you are calculating mean square speed? A, B, C. Which one? The B, right?
B, yes.
B is your mean square speed. Okay, let's see. 7 molecules traveling in 200, 300, up to 800 meter per second randomly. Find their mean speed. Mean speed easy. What do? You add all of them, divide by the number of particles, right? 7. 200 plus 300 plus 400 plus 500 divided by 7. You get the mean speed, 500 meter per second. Okay. But now the focus is the B. How do you find mean square speed? Mean square speed. Square the speed. Square all of them. Okay. Square up to 800 square and find the mean of them. That means divide by n, 7. In this case, 7, right? 1, 2, 3, 4, 5, 6, 7 particles. So 7. The answer you get here. This is your mean square speed. Is mean of the square speed. So you get 290,000 meter per second. Okay, this is a very important speed. You need to know. Okay, third, root mean square speed. Root mean square speed. Root mean square speed is what? Root of the mean square speed. This is root mean square speed. Root mean square speed, just whatever value you got here, root it lah. Root, that's your answer here. So get 539 meter per second. Okay, root mean square speed in statistic lah. In statistic, okay, they will find the mean speed. They will find the root mean square speed. They'll find the mean speed, and they find the root mean square speed, both like an average value. Okay. Normally sometimes they use root mean square speed, sometimes they use mean square speed. If a value you have a positive and negative, like one particle move to the right 200 meter per second, the one move to the left is negative 400 meter per second. If you find mean square speed, the value can cancel. 200 plus negative 400 can cancel. So to avoid cancellation, you have to square it to make them positive. then you root it back, kind of like an average. So that's why you use root mean square speed. Okay, root mean square speed is like the mean speed, but we just avoiding cancellation by squaring them. Okay, RMS value we call it. Okay, so but out of these three, the one really intact to the formula is mean square speed. Okay, square the speed, average of that speed. That's your mean square speed. Okay, so hope all of you got the three answers correctly. Anybody don't understand? Okay, so far okay, huh? Okay. So then, as I said, comparing the two formula, we got the kinetic energy formula. Half mc squared is 3/2 kT here. A big breakthrough in science. The kinetic energy is found to be proportional to temperature. This is only materialized with the existence of PV equals to 1/3 nmc squared by theoretical scientists. Okay, so yeah. So this is the topic of ideal gas law. We're done with the topic already. Okay. So we start from what we learned today. We learned about Brownian motion. Observation is the dust particle move in a jerky manner. Okay. And what is the conclusion? The smoke particle collide with the air particles because therefore air particles move in a air particles move randomly. Okay. And we talk about the assumption. Assumption must remember at least three. Remember the one, what you call neglected one. The intermolecular force is neglected. The molecule volume is neglected compared to the volume of the gas. Then you say it moves with a constant, what do you call it? Move with the collisions are elastic collisions. Okay. And yeah, the gas consists of particle molecules. So you need to know at least three, the kinetic theory of gases. Then the pressure gas formula has been derived, a long derivation in your A2 syllabus, which end up getting PV equals to 1/3 nmc squared. And density, then we compare them to find the kinetic energy. Okay. So any questions so far? No questions, eh? Okay. So as usual, let's recap back. What are the topics? What are the formulas you learned in this topic? PV over T is constant. Then PV equals to nRT. Then PV equals to nKT. Then PV equals to 1/3 c squared. Then finally, what do you learn? P equals to 1/3 rho c squared. Another one, kinetic energy is found to be 3/2 kT. Out of these entire equations, the last one is the most important. Okay, 3/2 kT. These three, I think these three, the first formula you learn in your SPM or maybe O levels. Okay, this entire thing you learn in your A levels. Okay. Any questions? So you have about 6 equations you learn. Okay. So if you don't have questions, okay, let's discuss some question from the slide. Okay. So after we learn this equation 3/2 kT, one example. Look at the question, look at the solution. Try to understand. So estimate the root mean square speed. That means they are looking for root mean square speed of Air molecule is 273 Kelvin. This is the temperature. At 1 atmospheric pressure is given. If the density of the air under this condition is this much, rho given. So what is the mean square speed at that moment? So pressure equals to 1/3 rho c squared. So just substitute. So you get the they want root mean squared. Sorry, root mean squared. So from this formula we can find mean square speed. Then the mean square speed, you go and root it, you get root mean square speed. Okay, it's found to be 502 meter per second. Okay, so the formula I have to use is, of course, pressure equals to 1/3 rho c squared. The speed here given here, this speed is mean square speed. Many times I'm repeating this because don't get confused. The mean square speed is the one attached to the formula. All formula they have, all are mean square speed. But in exam, they might ask root mean square speed. So you find the mean square speed first, then you root it. Okay. You go to the another one. Okay. 1 minute for you. Look at the question, look at the solution. Okay, guys, so can you understand the flow? The density is given. Find the mean square speed. They want the mean square speed. They want this mean square speed of the nitrogen molecule in air at STP. And as it is the mean kinetic energy of the molecule. Okay. So at STP, normally the pressure and temperature will be given to you. So P equals to 1/3 rho c squared. Rho is given. We're looking for C. The pressure is the density is 1.25. The pressure is the 1 atm lah. STP 1 times 10⁵. So you get the mean square speed. Okay. Then if you know the mean square speed, we can work out the kinetic energy. Kinetic energy is 1/2 mc squared. Okay, but m is must be mass of one particle. They want mass. They want which energy? Oh, they want the mean kinetic energy of a molecule. So one molecule. So 0.028. 0.028. Your chemistry knowledge. The molecular mass is 28 gram. 28. That means what you should understand. 28 gram is for 1 mole. So what is the mass of one particle? So 28 gram changed to kilogram divided by the Avogadro constant. So m/na gives you the mass of one particle. Then you can use half mc squared to get the answer. 5.58 times 10⁻⁻21. Okay. Any part you don't understand? Okay, so this is the something new formula. How do you use it? Mean square speed. Don't normally go for mean square speed. Okay. Okay. Another one. Look at the question. Try to figure out. Look at the solution. Make sense? Find the average kinetic energy of molecule in air of 300 Kelvin. So as I said, whenever they say kinetic energy, the formula must come to your mind is 3/2 kT. if you know the temperature. Temperature, they already say 300 Kelvin. Just put 300 Kelvin. Boltzmann constant 1.38 times 10 302. So this is the energy should possessed by the particle. Okay. So in a container, if you have oxygen, you have a CO2, you have a nitrogen, if all of them exposed to the same temperature, means all of them have the same kinetic energy. Okay. Their mean square speed, of course, different. The more heavy one, more massive, will has a less mean square speed. But they all definitely possess the same kinetic energy. Okay. So you have many examples. The last one. Okay, let's go for the last one. This is the last one. Okay, 1 minute for you guys. Last one for today. Okay, so I hope you get the solution. In order to achieve a fusion reaction, the temperature of the order is 1 times 10 power of 7 Kelvin. So yes, for fusion happen, the temperature must be million degrees Celsius, which only occurs at the center of the sun. At the core of the sun, this temperature is attained due to high pressure. So the hydrogen and hydrogen atom can merge, fusion happen. At that moment, what is the mean square speed? Estimate the mean speed, or they want the mean speed. It's actually a root mean square speed. This is a root. This is not mean square speed. Mean speed means, as I say, mean speed is like RMS value, root mean square speed. Mean speed, root mean square speed. We can say it like the same. Root mean square speed. So half mc squared equals to 302 kT. We find the mean square speed first, then square root it, you get the root mean square speed. So this is the root mean square speed, 3.56 times 10 power 5. Okay, temperature is enough to find the mean square speed. Square root it, you can get the what do you call? You can get the average root mean square speed. Okay, then that's it. This is ideal gas. Any question, guys, from here? Okay, so we have another 1 hour, right? So we'll be doing questions about this ideal gas. Okay, but we start doing the question at the back here. We will find the working, okay, by using the formula for the next hour. Okay, so I stop here. See you back later, 4 o'clock.